Hello. Welcome to Lecture 9 of Privacy and Machine Learning and Statistics. In this lecture, we're going to talk about a slight generalization of the definition of differential privacy. That's sometimes called approximate differential privacy or epsilon delta differential privacy for reasons we're going to see. And this definition is going to be slightly weaker than the standard definition of differential privacy, but it's going to allow us to do a lot more. So we'll see some examples of what we can do with it in this lecture, and also see more in the next lecture when we talk about composition. And in particular, what we're going to build up to in this lecture is the Gaussian mechanism, which is a twist or a variant of the Laplace mechanism that's going to allow better utility in some settings. So remember, epsilon differential privacy says that we have some algorithm that takes a data set of size n and maps it to some output in a space y. And the condition says that for every pair of neighboring data sets x and x prime, and every possible event we could observe, the probability of that event under a of x can't be too much bigger than the probability of that event under a of x prime, up to this purely multiplicative factor of e to the epsilon. Okay, so we require closeness in this multiplicative sense. And the reason we want that is for a strong kind of semantic guarantee that says if you condition on seeing a particular outcome y, then what we believe about some particular input xi shouldn't change too much depending on whether y came from a of x or a of x prime, where in this case x prime is x without the data xi at all. Okay, so the reason we want this multiplicative definition is that it allows us to make some statement about what happens when you condition on a particular output. And basically says that since you don't know whether that output came from x or x prime, the posteriors aren't too different. Okay, but this definition is very stringent. In particular, what it means is that if some event has probability 0 under a of x prime, then it has to have probability exactly 0 on a of x. Okay, so for example, there can't be any events that happen with 0 probability under one data set and non-zero probability under a neighboring data set, no matter how small that non-zero probability is. So it's kind of natural to wonder, what if we could relax this definition a little bit sort of that we don't have to worry about these events that have large multiplicative differences in the probability, but sort of don't really happen that, are extremely unlikely to happen under either data set. Okay, so in the semantic language, this has some output y that has, where conditioning on y would cause our beliefs about xi to change a ton, but we're so unlikely to see that y anyway that maybe we don't care. And roughly speaking, epsilon delta differential privacy is an attempt to kind of capture the intuition that we should be okay with such mechanisms. And this is also sometimes called approximate differential privacy. And it's exactly the same definition, except we now have an extra parameter delta, and we say that the probability of the event e under a of x should be no more than e to the epsilon times probability of that event under a of x prime, plus some additional additive term delta. Okay, so this allows for a situation where the probability that a of x prime is in E is 0, and the probability that a of x in E is non-zero. It could be delta. Okay, so I should say first of all that epsilon dp, as we understand it, is sometimes called pure dp, and is exactly the same thing as epsilon 0 dp under this new definition. And as I said, this epsilon delta definition is sometimes called approximate, so sometimes people refer to pure and approximate dp. Personally, I don't really like this terminology because it suggests that epsilon dp is somehow substandard, which I don't agree with, but it is a convenient terminology, so I will go with the crowd and use it. One there's a couple points we should make about this definition. One of them is that delta should be very small. Okay, and the reason is because unlike epsilon, we should think of delta as potentially being like the probability of a total privacy failure. So this definition could be satisfied by mechanisms that just have some probability delta of just outputting the entire data set. So we want that probability to be very small. So you should think of delta as, 2 to the minus 128 or something, or 2 to the minus 60, or maybe at least 2 to the minus 20. Of course, the smaller delta is, the more restrictive the definition is, but we want delta to be very small. This is in contrast to epsilon, where we think of epsilon as being maybe 1/10 or 1/2 or maybe even 1. Okay, so delta has to be very small. Or delta should be very small for this to be a meaningful definition of privacy. The other thing that we should say is that many of the properties of epsilon 0 differential privacy are still true for this definition. So I'm not going to list every property. In fact, we haven't listed every property of epsilon 0 differential privacy, but two that are important just to establish that this is sort of broadly similar to epsilon 0. So one is post-processing. Still holds. Okay, so if I post-process the output of an epsilon delta differentially private algorithm, the result is still an epsilon delta differentially private algorithm. So that's good. Okay, we haven't broken anything too badly because we still have post-processing. And lastly, we also have a composition theorem, which says, if A1 is epsilon 1 delta 1 dp, A2 is epsilon 2 delta dp, then kind of A1 following A2 is epsilon 1 plus epsilon 2, comma delta 1 plus, is epsilon. So if I take the composition of two algorithms, I can just sum up the epsilons and sum up the deltas. And this holds even if the composition is adaptive. So just like with pure epsilon dp, A2 could actually take the output of A1 along with the data set, and we would still be able to just add up the privacy parameters. Okay, but just looking ahead, epsilon delta differential privacy actually satisfies stronger composition bounds when we compose lots of epsilon delta differentially private algorithms. We can actually argue that the privacy parameters don't just add up, they actually grow slower than linearly in the individual parameters. So that's going to be the subject of the next lecture, and that's one of, I would say, the best reasons to study epsilon delta differential privacy, because even if you only like designing algorithms that are epsilon 0 differentially private, when you compose many of them, you're going to get effectively an epsilon delta differentially private algorithm where allowing that non-zero delta makes the epsilon much, much smaller. So we get sort of a much more precise understanding of what's going on under composition if we allow this small delta. Okay, so that's a little teaser for next time, but just as a sanity check, we still have basically the same composition theorem we had for pure differential privacy, where the epsilons and deltas now just add up. All right, so before we see our first example of a kind of epsilon delta differentially private mechanism that actually meaningfully takes advantage of epsilon delta, I want to talk a little bit about an important technical point about proving epsilon delta differential privacy. So the slide has a lot of writing on it, so let's go through it step by step. So the first part is just the definition of epsilon delta dp. Now, if you remember, when we tried to prove that a mechanism was pure differentially private, or epsilon 0 dp, we often used the following fact, which says that it's enough to consider events E that are just singletons. So what we often did in the proof is we just said for all individual outcomes Y, the probability of getting Y under AX wasn't too much bigger than the probability of getting Y under A of X prime. And we said that that actually implies the definition as it was written, where we don't just ask about individual outcomes Y, we ask about events or sets of outcomes E. Okay, so we could have just equivalently defined epsilon 0 dp in terms of these single outcomes Y. Okay, it's very important to remember that that's not going to be true for epsilon delta dp. Okay, so if you can show that for every individual outcome Y, the probability of getting Y under AX is not too much more than is smaller than e to the epsilon times the probability of getting it under AX prime plus delta, that does not imply the definition of epsilon delta differential privacy. Okay, and intuitively the reason is that when I take a sum over all of the elements of the set E, I have to add up the deltas, and I could be adding up a large or even infinite number of deltas. Okay, so it's not enough to consider just singleton events. We really have to focus on arbitrary events E when we prove approximate differential privacy. So I'm saying this for two reasons. The first is just to remind people to avoid a common mistake, not to use this common simplification that we used for pure DP, but also to give a chance to talk about one common way that we do try to prove that something is epsilon delta differentially private. And the sort of idea is as follows. So imagine you draw two curves. The black one is the probability distribution of A of X, and the red one is the probability distribution of A of X prime. And what epsilon delta allows is it allows for the possibility that there are some regions where these two probability distributions are not within an e to the epsilon factor of one another. Right? And that's what I've highlighted and called the bad region here. Okay, and what we can do is we can basically argue that if you look at all the possible outcomes Y, it's enough to argue that the black and red curves are within an e to the epsilon factor at most points, at most outcomes Y. So you want to show that there is only a small set on which the ratio is not bounded, and the probability of getting this event under the black distribution should be small. So like this black region should be small. Okay, like this black region is like probability AX in the bad set. And as long as that thing is small, you'll get epsilon delta dp. Okay, so to formalize this, we'll fix some pair of data sets X and X prime that are neighboring, and we'll define the good set to be all of the Y's, all the possible outcomes of the mechanism, where Y is not too much more likely to occur when the data set is X than when the data set is X prime. Okay, so that's what this condition says. It says that the probability of getting Y under AX should not be too much bigger, should not be more than an e to the epsilon factor larger than the probability of getting Y under AX prime. Right? And we'll define the bad set to just be like the complement of the good set. So these are the ones where you are much more likely to see Y when the data set is X than you were when the data set was X prime. All right, so if I wanted to prove that a mechanism is epsilon 0 differentially private, what I have to argue is that every single Y is in the good set and no Y's are in the bad set. but epsilon delta allows me to have some y's in the bad set. And the lemma we're going to prove is that if for every pair of data sets x and x prime, the probability that a of x outputs something in the bad set for the data sets x and x prime should be at most delta. Okay, and one small thing to note here is that the good and bad set depends on x and x prime. Okay, it's not that it has to be like one bad set of y's, it just has to be one bad set of y's for every pair x and x prime, but you can choose a different one for every x and x prime. Okay, so what the lemma says is that it's enough to argue that if you define the bad set for a particular x and x prime, the probability that a of x lands in that bad set should be at most delta. And if that's true, then a is epsilon delta dp. Okay, so the proof is kind of worth looking at. So what we're going to do is we'll write the probability that a of x is in some event e, where e is some arbitrary event. We'll split it up into the probability that it lands into the intersection of e and the good set, and e in the bad set. And I'm dropping the x and x prime from good and bad just to make this a little easier on me to write. Okay, so first of all, like the first thing to notice is that the probability of landing in E intersect bad is at most the probability of landing in bad. Okay, so for all we care, like E might contain the whole bad set. And by assumption, that second term is at most delta. Okay, so that's kind of going to be where the delta comes from. For the second part, well, if we only look at elements in the good set, so first let's write this probability as the sum over all of the y's that are good. And here's we'll use the property of the good set, which says that each of these individual probabilities is no more than e to the epsilon times the probability that a of x prime is equal to y. So taking the sum again, we get that this is the e to the epsilon times the probability that a of x prime is in E intersect good. So we're almost there. What we'd like to get is E, not E intersect good, but intersecting with good can only lower the probability. So this thing is at most E to the epsilon probability ax prime in E plus delta, which is exactly the thing we wanted. So we started with this probability a of x is in E, and through a series of slightly slanty calculations, we said that this was at most probability e to the epsilon times the probability a of x prime is in E plus delta. Okay, so this lemma is going to be important. This is going to be how we're going to prove things are epsilon delta differentially private. We're going to do it by arguing that for every particular pair x and x prime, there's some small set of outcomes that are in this bad set, that they're much more likely to come up under x than under x prime. But you're unlikely to be looking at one of those things. If you draw the outcome from a of x, you're very unlikely to be seeing one of those things. Okay, so that's going to be how we prove it. Note that if we set delta equal to 0, then this definition is like equivalent to epsilon 0 differential privacy. It's not equivalent for epsilon delta, but it's sort of roughly kind of equivalent. It has sort of a very similar. It's not quite the same definition, but it goes one way. It goes the way we want it. So if you can show this, you can get epsilon delta. Epsilon delta does not imply that the probability of being in the bad set is at most delta. Okay, good. So let's, before going on, let's just see one example of something you can do with epsilon delta differential privacy that you just can't do with epsilon 0. So that we wouldn't relax the definition unless we actually could get something from it. We're not just relaxing it for fun. So let's see a first example of something where we can actually win by using a delta that's greater than 0. So, if you remember our old friend, the Laplace mechanism, we add noise from the Laplace distribution with some scale parameter lambda, and the standard deviation of that distribution is proportional to lambda. But it has unbounded support, so there's some probability that we see any real number as the outcome. So if we add noise from this Laplace distribution, we have some probability that we get anything as the output, no matter how bad the error would be. Okay, so and one can argue, although we haven't really seen the tools to do it, that that's inherent for anything that satisfies epsilon 0 differential privacy. Okay, so what if we want to have some guarantee that the error will never be too big? There'll be some upper bound on the error that we could get. Well, we can consider adding noise from something called a truncated Laplace distribution, which has the scale parameter lambda and an extra parameter tau. And we'll think of tau as much bigger than lambda. So when that happens, this distribution still has standard deviation proportional to lambda, but now we're going to just cut off the distribution at minus tau and plus tau, and we're just going to zero out the probability mass outside of that. So we're just going to take the distribution, and we're basically going to just chop it off or truncate it so that it never takes a value smaller than minus tau or bigger than tau. So we can get a variant of the Laplace mechanism where we add noise from, instead of a Laplace distribution, a truncated Laplace distribution, where lambda is proportional to the sensitivity over epsilon, and the truncation parameter is going to be log 1 over delta. So we're going to take the distribution with scale 1, and we're going to chop it off at log 1 over delta, and then we're going to multiply that whole thing by delta over epsilon. Okay, so we'll cut off the tails, and what you can show is that this algorithm satisfies epsilon delta dp or epsilon order delta dp. So I think you have to make it 2 delta or 3 delta or something like that. So this is a way to get differential privacy, epsilon delta differential privacy, with the same kind of expected error as the Laplace mechanism, but with no chance of getting an extreme value. So we have that the noise is never going to be bigger than delta over epsilon times log 1 over delta, where the first delta is the sensitivity and the second is the delta in the dp. Okay, so if we tolerate some small delta bigger than 0, we can get a guarantee that the noise will just never be too big. And one way to think about this is that the Laplace distribution has some small probability of outputting something that's totally ridiculous, and we're kind of trading that small probability of outputting something totally ridiculous for a small probability of losing privacy. And there's some settings where maybe that's reasonable. So I think we'll give this as an in-class exercise to prove, but let me just sort of sketch it with a proof by picture, which is that if you draw, say the black curve is a truncated Laplace, and the red curve is that same truncated Laplace shifted over to the right by 1, then what you can see is that the ratio is no longer bounded because there's this little region where the black curve has non-zero probability and the red curve has 0 probability. But because of the way we chose the truncation parameter, the probability of landing in that region is like this, the mass of this little black area, which is going to be small. So because we chose this truncation parameter to be about log 1 over delta, the probability of that bad landing in that little black area, or the integral of that little black area, is going to be small. Okay, so that's sort of the gist of the proof. So this lemma that we proved, it makes it kind of nice to translate kind of this picture and this intuition into a proof. So that's it for this video. In the next video, we'll talk about the Gaussian mechanism, which is going to be the sort of main tool we use for epsilon delta dp.